Okay, so I was told to be on the stage for the light because of the light. So it is my pleasure to present to you our next speaker, Tatiana Andreeva. And the title of her talk is The Surjectivity and Injectivity of Convolution Operators, some interdisciplinary corollaries. I'm sorry.
Well, dear colleagues, it's a great honor and pleasure for me to present my today's talk devoted to convolution operators defined on special weighted functional spaces. These spaces are constructed as follows. First of all, suppose that G is a bounded convex domain in complex plane that conveys origin. Denote by H from G the space of all functions that are holomorphic in G. Let us consider an auxiliary sequence phi. There's something with sound, I think. Let us consider an auxiliary sequence of phi of some positive convex monotonically increasing function satisfying the following preconditions. These conditions are similar by those used by Nabelkov, with the only difference that Nabelkov constructed the space endowed by projective limit topology, and we use the inductive limits. The first and the second one are just natural. They imply the connectivity of differentiation, and the third one has a technical character and does not put any strong restrictions. Further, let weight Vn be the function phi n from an argument logarithm 1 divided by distance from a point of a domain to the boundary of this domain. Thus, we define the main weight sequence V. To each weight Vn, we assign the following Banach space of holomorphic functions Hn, and let Vh from G be the inductive limit of this space sequence. Vh is our main weight space. Further, suppose mu is an analytical functional in C carried by a convex compact set K, and consider the convolution operator. It is a well-known fact that it maps continuously the space of functions holomorphic in G plus K into the space of functions holomorphic in G, and also consider the corresponding non-homogeneous convolution equation y.1, where the solution is from the space of functions holomorphic in G plus K, and the right part from H from G. Now consider the same operator defined on the weight space Vh G plus K and mapping in into or onto Vh from G. Speaking about continuity, we use into. Speaking about surjectivity, we use onto. The questions of this talk are: when the convolution operator continuous or surjective? When does the non-homogeneous convolution equation have the unique solution? The result for a convolution operator are given in terms of its analytical symbol, the Laplace transform of the functional. Let us recall that for any functional mu, its Laplace transform is given by hatchet mu from zeta. It's an entire function of exponential type satisfying the following condition of growth at infinity. Here, hk is the support function of the compact k. To obtain the surjectivity criteria for the convolution operator in terms of its Laplace transform, we have to consider particular cases of weight sequence V. We consider in this talk the space of exponential power growth and normal type defined by the following weight sequence Vn. Also, let us recall some useful definitions. Let phi be an entire function of exponential type. Its radial indicator is defined as follows. We use the multidimensional definition radial indicator instead of a classical indicator just to simplify the proof, just only for these purposes. For each analytical functional mu with the defined properties, the radial indicator of its symbol is less or equal than the support function hk. And the first of the restrictions on symbol is the equality instead of inequality here. The second restriction is the complete regal growth condition. Namely, we will say that the entire function phi of exponential type satisfies the S alpha condition of growth if for every point zeta sufficiently far from the origin, there exists zeta prime from a rather small neighborhood of zeta in which the function phi satisfies the following lower estimation. Please note that this condition is stronger than the completely regular growth condition. Finally, we're about to present the main result of this talk, the surjectivity criterion. Suppose mu is analytical functional in complex plane carried by a convex compact set K. Hatted mu is from the auxiliary space VHK infinity of the entire functions. Then the convolution operator is surjective for every bounded convex domain G if and only if the radial indicator of its symbol is equal to hk, the support function of k, and hatted mu satisfies the condition S alpha of radial growth. Further, let us consider the non-homogeneous convolution equation 3.1, where the solution is from our weighted space VH G plus K, and the right part is from the weighted space VH from G. Suppose, furthermore, that mu is surjective. It's a well-known fact that the convolution operator is injective if it has a non-zero symbol in G. The question is, can the equation have a unique solution otherwise? One of the answers is, let D be a neighborhood of origin such that its closure is embedded into our domain G. Let D contain the finite number of zeros of the symbol hatted mu, and let M be a number of zeros of the symbol of mu hatted in D, taking into account their multiplicity. We consider the Cauchy problem 3.2, 3.3. And then for each right part from VH from D, not from G but from D, there exists a unique solution from VH from D. It's one of the answers. Let us consider another application. It is interesting to consider convolution for with some particular operators. For instance, within the subject on fractional integral differentiation. One of the models within the framework of fractional integral differentiation is the Riesz integral differentiation. And Riesz potentials fulfills the negative fractional degrees of Laplace operator, acting on the space of functions of many real variables. The Riesz potentials seem to be interesting to extend them on the case of complex analysis, and such an attempt is made here. Let us consider mu, an analytical functional that is defined by the measure psi d lambda. Lambda is Lebesgue measure here, and assume that it has the following Laplace transform, a function m from an argument zeta. The inverse Fourier Laplace transform of psi considered as a function of two real variables is the following function, and it is an analytical function of two complex variables. Though we consider the functional mu such that there is the correlation between the defining function psi and the symbol m. Here it is. Now let us recall the Fourier transform and inverse Fourier transform of an ordinary function phi, and also the translation property of on a vector x null fixed in R2. In Riesz analysis, the Fourier transform of a radial function is of great interest, and generally speaking, the Fourier transform of a radial function is a Fourier transform of a generalized function from the class of Schwarz functions. But in this particular range of the parameter alpha, the Fourier transform of a radial function can be computed as a Fourier transform of a normal, ordinary function via the Bochner's formula. And we get this following equation. Roughly speaking, the Fourier transform of a radial function is also a radial function, but from another degree. And the right part here is the Riesz kernel K alpha. Here it is. The convolution with this Riesz kernel fulfills the negative fractional degrees of Laplacian, being an operator acting on a class of functions of real variables. Moreover, we need not only a functional that is somehow connected with Riesz kernel, we need functional mu with rather good properties, for example, with non-zero symbols. And to guarantee this, we should guarantee the translation property. Please see this framed expression. This expression can guarantee that the Fourier image of a radial function satisfies this translation property. And thus, we can calculate the symbol of mu, m out from zeta, as a function in this exact form, from an argument zeta complex and parameter zeta that is also complex. It uniquely defines the functional, which we suggest to consider as Riesz potential type operator. And finally, under the corresponding conditions of the presented theorems, the convolution with the Riesz potential type operator mu defined by M is surjective or bijective, is defined from the concrete theorem in the spaces of Lamarckian functions of preset growth. So, I'll skip this. That's the end of my part. It's not working, but I can hear it.
Thank you. Oh, gracias. You have a question? No?
Excuse me, what you can say about the Bessel potential? Bessel potentials, because it's quite nice generalization. Riesz potential. So it's the same book of Samko, you can see this. Did you study it?
I haven't considered that.
Because it involves McDonald functions and very nice behavior. It's similar to Riesz potential.
You know, it's rather new result, so I haven't worked.
It could be a good project, I think, to apply your theory to Bessel potentials.
Thank you for this idea.
Thank you. Any other question or remark? So I will thank you in two ways for your very nice talk, and you enable us to gain some time, so it's not usual. So thanks again.